Welcome. In this session in linear data analysis, we'll explore the quadratic form of a symmetric matrix. Let's consider a matrix that has all real numbers, m rows, m columns, and that the matrix is a symmetric matrix. Then, from the spectral theorem, from a particular form of the spectral theorem, we know that we can write this matrix as an orthogonal matrix times the diagonal eigenvalue matrix times the transpose of the orthogonal matrix. And so one basis of these real numbers is the columns of this orthogonal matrix, which we'll refer to as Q. So let's suppose that this is Qj. So any vector U that has m entries can be written as a unique linear combination of the eigenvectors. Let's say that we'll use the value alpha 1, the real number, times the first eigenvector plus alpha 2 times the second eigenvector, and so on until we have used all of the eigenvectors that are in the basis. What happens when we take this any vector u, so we're assuming it's non-zero, that if we take any vector u and we multiply it by b, what do we get? Well, because u has this linear combination of the eigenvector basis, what we can do is we can multiply b into this equation. So the first one is b times alpha 1 times q1. That's the same as alpha 1 times b times q1, and that's the same as lambda 1 times alpha 1 times q1. Likewise, if I multiply b into this, the next one is b times alpha 2 times q2. Using the same reasoning, I can say that that is lambda 2 times alpha 2 times q2, and so on until I have expressed all of the basis vectors for the coordinate space of size n. What happens when I multiply this product by U transpose? So let's go through this. So U transpose times B times U will equal, well, one way that we can reason this out is, let's suppose that we're just dealing with size 2 entries. So if we put this in, then U transpose, this is a scalar, this is a scalar, so the transpose would be Q1 transpose plus lambda 2 alpha 2 Q transpose. If I take Q1 transpose plus Q2 transpose times these, what do I get? Well, I would get Q1 dot Q1 plus a Q1 dot Q2 term, but the Q's are the columns of an orthogonal matrix, so Q1 dot Q2 is 0. So if I, now let me think this through for the whole term. If I take Q1 transpose times this, I'll get something for here, and then the dot product of Q1, Q2, etc., Q1, Qm, all of those are 0, so they cancel out. So the only things that don't cancel out are these, we leave this eigenvalue, and now what doesn't cancel out is the Q1 dot Q1. So that is lambda 1, and then I'll have U transpose is alpha 1 Q1 transpose, so that alpha 1 gets squared, and then I have that as Q1 dot Q1, which is 1, and so on. And then this term would be lambda 2 times alpha 2 squared times Q2 dot Q2, and so on until I have expressed all of the terms in this linear combination, which is now not a linear combination, now it's a scalar expression. And so that has to equal, so this term is 1. Q1 dot Q1 is 1. Why? Because it's a column of an orthogonal matrix. Q2 dot Q2 is 1, and so on. And that means that I can write this as lambda 1 times alpha 1 squared plus lambda 2 times alpha 2 squared, and so on to lambda m alpha m squared. And this critically depends upon having an eigenvector basis which requires diagonalizability, which is always true for a symmetric matrix. So this doesn't apply to any matrix. For example, if the matrix isn't square, we can't even create this quadratic form. And if the matrix is square but isn't diagonalizable, none of this works out. So there's something very special about symmetric matrices. Right? Now, let's take a look at this sum carefully. Alpha 1 squared has to be greater than or equal to 0. Alpha 2 squared has to be greater than or equal to 0, and so on. So each alpha j squared has to be greater than or equal to 0. So what is a requirement for U transpose? So let's say if U transpose B U is greater than 0, then what statement can I make about this sum? If this sum is 0, and this sum is the sum of real numbers times non-negative numbers, then this sum, to be greater than 0, that means that each one of these has to be, if this is strictly greater than 0, then each one of these has to be strictly greater than 0 in the general case. Perhaps in a particular case, you might get some alpha j squared is exactly equal to 0, but in the general case, and we're considering the general case, so in general, then in general, then comma, in general, comma, each eigenvalue has to be greater than 0. Likewise, if the quadratic form of this symmetric matrix is greater than or equal to 0, then I can conclude that each eigenvalue has to be at least 0 and possibly greater. This is how we reason things out, and if there is no restriction on this, then we get into that indefinite case, which requires some fairly careful reasoning, and we won't be using indefinite matrices intentionally very often. Now, let's consider a special case of a symmetric matrix. So let's consider something that occurs in linear data analysis a lot. Suppose we have a general matrix. So this has real numbers and it has m rows, and now we'll let it have any number of columns except what we'll say with columns linearly independent. So what can I say about that? Well, let's reason this out. If there are n columns and they're linearly independent, then that means that the rank of A is the number of columns. So A has to be full rank. And that means it's either a square matrix or n is less than m, and we call that a tall, thin matrix, one that has more rows than it has columns. So if A is a full rank matrix, square or not, let's think about this. What does a U that's non-zero map to? Well, let's say that it maps to some vector y. So let's say y equals A times U. So what is the norm of y? Well, let's look at the norm squared. So the norm of y squared is, that would be y transpose y. And that's because the norm of y is the square root of this, so the square of the norm is this. Well, what is y? Well, that is, so y is A times U transpose times A times U. And by the rule of transposition, that equals U transpose A transpose A U. Now, the norm of y has to be greater than 0 because A is full rank. So A is full rank. That means that that U can't be in its null space. And that means that y must be non-zero. So let's add that in. With y not equal to 0, because the null space of this matrix, it being full rank, the null space has to be trivial. So now, y is non-zero, so the norm of y is that, and the norm of a non-zero vector has to be strictly greater than 0, and that means that this matrix, A transpose A, has to be symmetric by construction. And now, if the quadratic form of any matrix U with this matrix is greater than 0, which we just showed it has to be, then that means that this matrix has to be symmetric, positive, definite. Let's work through a simple example to be sure that we get this. So suppose that our matrix A is this. First column is 1, minus 1, 1. Oh, second column is 1, 1, 1. So A transpose will be, its first row will be 1, minus 1, 1, 1, 1, 1. Oh, is this full rank? Well, yes, because this column cannot be a scalar multiple of this column. So now, what is A transpose A? Well, that would be 1 plus 1 plus 1 is 3. Then its second entry would be 1 minus 1 plus 1 is 1. Its 2, 1 entry would be 1 minus 1 plus 1 would be 1. and its 2, 2 entry would be 1 plus 1 plus 1 is 3. And we can verify quickly that for this matrix, its first eigenvalue is 2, and its second eigenvalue is 4. And what are the eigenvectors specifically? Well, they had better turn out to be an orthonormal basis, and indeed they are. That the first eigenvector is proportional to 1 minus 1, and the second eigenvector is proportional to 1, 1. So this is a full rank matrix. A transpose A is symmetric by construction, and then it's also positive definite because this original matrix is full rank.